Okay, so let us start our session today. We'll quickly revise the topics we covered in the previous session and then we will continue today's topics. Okay, today we will complete week 9 topics. Okay, fine. So in week 9, mainly we are looking at multivariable calculus. So far we have seen what is a scalar valued function and a vector valued function. Okay, so for a scalar valued function and vector valued function, for both of these the domain is in Rn. Okay, and the codomain, you see, for scalar valued it is just real numbers and for vector valued it is Rm. Okay, so they are the images of vector valued functions, they are all vectors and here they are all scalars. Okay, and what are the arithmetic operations we can define for this functions? Here you see that for a multivariable function f and g, you can define the sum, the scalar product. Okay, but when it comes to multiplication or division, be careful that your m should be equal to 1, and also of course for d your denominator should be non-zero. Okay, so remember that your m should be 1 for product and quotient. Okay, fine. And what are curves in Rm? Curves in Rm refer to the range of the function f from d to Rm, right? So they are just range of this d to Rm. Okay, so you see that. So here these are conics in R2. Here this is helix, and this is some other figure. So all these are different curves in Rm. Okay, and what is rate of change with respect to a particular variable at a point? So rate of change at a particular point. So you consider a multivariable function f of x1, x2, xn. Okay, with I guess you all remember what is an open ball, right? What is an open ball? Open ball is something like a sphere in R3 and a circle in R2, right? The set of all x in Rn such that norm x minus a or x set of all x till, this is a notation, right? Less than or equal to R. So this is an open ball with center at A and radius R. All right. Okay. So then the rate of f at A with respect to the variable xi is limit h goes to 0, f of a tilde plus hei minus f of a tilde by h. We have explained how we have obtained this, right? So this basically reduces to limit h goes to 0. So your a tilde is nothing but a1. So f of a tilde plus hei means only the ith coordinate you have f of a1. Only in the ith coordinate you have ai plus or plus h. So 1 times of it going to be the same minus f of a1. Only the ith coordinate there is a change. So you see this is nothing but a derivative along the ith coordinate. Okay, so if you are in just R2, then if I is equal to 1, it refers to the derivative along x-axis, and if I is equal to 2, it refers to the derivative along y-axis, right? Okay. And we have given geometrical explanation of this partial derivatives of f of x comma y with respect to x at x naught, y naught. Okay. Fine. So here you see that partial derivative of f of x comma y with respect to x at x naught comma y naught means here what is that we are fixing? We are fixing the value of y. So this y value is fixed. So this is fixed. So you can consider this function as a function of just x alone by fixing y as y naught and then find the derivative that gives the partial derivative of f with respect to x naught, right? So this is your y naught value. So you have fixed this. You are not moving anywhere along y-axis. Only you are moving along the x-axis. Same way for partial derivative of f of x with f of x comma y with respect to y at x naught comma y naught. Again, what you are going to do? You are going to fix this x naught value and going to move your values along y alone. Okay, fine. So this is what is meant by partial derivatives. Next you see partial derivatives in general. So it is in R3 they have explained. So here in general for any Rn, here is the definition. Let f of, by the way, am I audible? Because the audience are quite very quiet. I'm just doubtful. I'm audible, right?
No, man.
Oh,
Yeah,
yeah.
you're
Yes,
audible.
ma'am, you are audible.
Okay, so let f of x1, x2, xn be a function on a domain D in Rn. What is the partial derivative with respect to xi? So in a particular direction, xi means you just add this hei, right? I have already written the expression for this, right? So here also they have written it explicitly. So this is the expression for partial derivative. Now you see partial derivative are very specific. They are considering this partial derivative along this different EIs. So what are these EIs? Along the different standard basis. So for example, in R2, if you take along x-axis or y-axis, or if in R3, x, y or z-axis. So along the different coordinate axis, you are considering the partial derivatives, right? But whereas directional derivative, you can consider any direction. For example, in R2, you can consider y is equal to x or y is equal to any mx or y is equal to, yeah. So all these different directions you can consider for directional derivatives. Okay. So in that case, what you have to do in that particular direction, you pick the unit vector. Okay, what is the unit vector in that specific direction you have to consider, that's all. Okay, so for example, I told you in case you have y is equal to mx, then how do you find the unit vector along this y is equal to mx? So your first coordinate, so this is in R2. So along this direction, if you have to find the directional derivative, okay, so the unit vector along y equal to mx, how do you find it? So your u is nothing but
x comma mx
x comma mx divided by
square root
square
of
root
x
of
square
x squared plus
m
n
square x
squared
square.
x squared. Okay, you have to simplify this depending on, if maybe you can put 1 or something and simplify the expression. Okay, depending on the specific values of m. Okay, fine. So remember, for directional derivative, if the vector u is not given as a unit vector directly, remember you should always convert it into a unit vector and then only do the directional derivative. Otherwise, it will be wrong. Okay. So remember that partial derivatives are special cases of the directional derivative where your u are nothing but the elements of the standard basis. Okay. Fine. Okay. So what are the properties of this directional derivative? So just like the properties of usual derivative, the directional derivative have similar properties. So let us consider a point A tilde. Okay, in the and you are considering the directional derivative at the point A tilde in the direction of the unit vector u for the functions f and g. Okay, so then what happens to cf plus g? You can simply split this addition, and then you get cfu of u at A tilde plus g in the direction of u at A tilde. Okay, so you can split it, and also the product rule, it applies the same. So you know that cu plus v the whole dash, what you do? Cu dash plus v dash, right? The same they have done here. Same way, uv whole dash, what you do? You write it as u dash v plus uv dash. The same they have done here also. Okay, and again for quotient rule also, it is exactly the same. What is u by v whole dash? You write v u dash minus u v dash by v square. The same is followed for quotient rule. The similar rules, you see, the similar rules are followed here as well. Okay, so nothing new. So the similar properties are following here as well, whatever you have seen for one variable cases. Okay, fine. Now find the directional derivative of the following direction in the direction of the unit vector u is equal to u1 comma u2. So here they have not given any specific numerical values. They have given arbitrary unit vector u is equal to u1 comma u2. Okay. So now what is the formula? Directional derivative of u of f. Okay. So u is given here. So how do you find it? What is the formula? Limit h goes to 0, f of What is the formula? Just
X
look
plus
at the formula.
X plus
See.
HU1.
Yeah. So you have x tilde plus h. Sorry, this is for
Partial derivative.
this is for partial derivative. For directional derivative, you have x1 plus u1h, x2 plus u2h, and etc. So the same you have to write here. If since we are doing it for the first time, I will write it for you. F of here only two variables. So x plus h u1, comma x, or maybe I can write it here. Y plus h u. The same I can write below also. Would have directly written x plus h u1, comma y plus h u2 minus f of x comma y, the whole divided by h. Now let us apply this function values here. So limit h goes to 0. So f of x comma y is x plus y. So for this term, it will be x plus hu1 plus y plus hu2 minus x minus y, right? And whole divided by h. So now you see that these terms will get cancelled. And so what will be remaining for you? So the remaining entries are limit h going to 0. You can take h commonly. So you get u1 plus u2 plus h. So you can write it as simply u1 plus u2. So this is the directional derivative of this function in the direction of the unit vector u1, u2. So whatever unit vector is given, so simply you have to take
Ma'am.
the sum of these vectors. That will be the answer. Okay. So let us find the directional derivative of this function. Here you see you have three coordinates. So the arbitrary vector you need to consider here is u1, u2, u3. Okay. So now again, this is limit h going to 0, f of x plus hu1, y plus hu2 plus comma z plus hu3 minus f of x comma y comma z, the whole divided by h. All right. Now this is equal to limit h going to 0. Now what is this function? Now the function value you see x plus hu1 into y plus hu2 plus y plus hu2 into z plus hu3 plus z plus hu3 into x plus hu1 minus xy minus yz minus zx, and the whole divided by h. So now you can write it as limit h going to 0. We have to multiply and expand this xy plus hu1y plus hu2x plus h squared u1 u2 plus yz plus hu2z plus hu3y plus h squared u2 u3 plus zx plus, yeah, what's the doubt? Did someone say
Sorry,
anything?
ma'am. Hello. Hello, ma'am.
Yeah,
Actually, the streaming or stop, I think.
yeah, can you please be louder?
The streaming,
Hmm.
the stop.
Oh, I don't know, the same issue happened last time also. Let me try it again, just a minute.
Okay.
Just a minute, I'm informing. As soon as I started streaming again, it went off. I don't know why.
Yeah, ma'am, no problem. It recording.
Okay, so just like in the previous class, maybe the recorded session will be posted later on. Okay, I don't know what is the issue. Okay, fine. So where were we? Yeah, so here HU1 times Z plus HU3 U1 minus XY minus YZ minus ZX. And the whole divided by H. Yeah?
H squared U3 U1.
X, Y, where? Here or where? Okay,
Before minus XY.
I don't understand. Where is that you are saying?
Before minus XY.
Yeah. Yeah, H squared. Yeah. Thank you. So now you see that you can strike out these terms. So, and in the remaining terms, you can take the H commonly. And what is remaining here is, if you take H commonly, then you see U1Y plus U2X. And first I will write the terms with just H as coefficient. Plus U3X. Here it's plus actually, right? Just a minute. Sorry. So here you see that, yeah, U3X and then U1Z. So these are all having H as coefficient. So when you are dividing it, it will get cancelled and all the remaining terms, this, and this. For this, you will get something here. Now, when you apply H going to 0, so this term will be 0. So what you are left with is this. So let us write this. So the coefficients with U1 into Y plus Z plus U2 into X plus Z plus U3 into y plus x. Okay, so these are this is the directional derivative of this function in this direction u. Okay, fine. All right. Now for the next question, I guess it is a little lengthy, but it's not difficult. Okay, again here an arbitrary unit vector we will take and find the directional derivative. Okay, so here you see that du of f is limit h going to 0 f of x plus hu1 y plus hu2 minus f of x comma y, and the whole divided by h. So here you see limit h going to 0. So this is sine of x plus hu1 into y plus hu2 minus sine xy, the whole divided by h. Okay, so now let us multiply this term inside. So you will get limit h going to 0 sine of xy plus hu1y plus hu2x plus h squared u1 u2 minus sine xy whole divided by h. So now let us consider this term alone as a and all the remaining terms as b. Now what is the formula for sine of a plus b? Yes, it is
Sin plus b
sine a
cos b
cos b
cos
and
sin
then
plus a
plus cos a
Cos
sine
A
b.
sin.
Okay. Let us apply this formula now. So if you are applying this formula, then limit h going to 0 sine xy into cos hu1y plus hu2x plus h squared u1 u2 and then plus cos xy into sine hu1y plus hu2x plus h squared u1 u2 minus sine xy. Now the whole divided by h. All right. Now as h goes to 0, what is happening in the numerator? Just observe. If h is going to 0, so here this terms become cos 0. What is cos 0?
1.
This is becoming cos 0, which is equal to 1. So this term will reduce to sine of x comma sine xy, right? And here you see when you make h going to 0, this is sine 0. So this term will become 0. So the whole numerator you see sine xy minus sine xy. So the numerator becomes 0 and the denominator also becomes 0. So if the limit of both the numerator and denominator gets 0, then what is the rule you can apply?
L plus b
L.
What is the rule?
L plus b
So you can use this rule. So by L'Hopital rule, you can do that. Limit h going to 0. So in the numerator, so we are doing the derivative with respect to h. So only this term you have to find the derivative. Sine xy will remain as it is as a constant. So here, what is the derivative of cos of some function? It is minus sine of this function, right? Minus sine of this value, hu1y. Maybe I'll write it as h times of some function. Okay, h times of something. And then the derivative of this. So what is the derivative of this with respect to h? u1y plus u2x plus h times of u1 2h times of u1 u. Okay, and then here cos xy and differentiation of sine is cos of h times of some function, and the derivative of that function here is, see, u1y plus u2x plus 2h times of u1 u2. This derivative is 0 because there is no h term involved here, and the denominator term also becomes 0. It becomes 1. The derivative of h with respect to h becomes 1. Now, as h goes to 0, sine 0 will become, this term will go to 0 as h goes to 0. And then what happens? So this whole term, the first term together will go to 0. What about the second term? This term will go to which value?
1.
Cos 0 will go to 1. Right? So what is
0.
remaining then?
Cos
Cos xy, and inside this term here this value becomes 0 into u1y plus u2x. Okay, so when you split it and write it, you will actually get u1 y cos xy plus u2 x cos xy. Okay, so this is the directional derivative of this function f of x comma y equal to sine x comma y. So whatever number if you are given some specific values for this vector, then you can just plug in u1 and u2 and you will get the answer. Okay. Fine. Up to this, is this clear for everyone? Finding the directional derivative using the formula. Okay, fine. So let us look at the next example. F of xy is x comma y is equal to xy by x squared plus y squared. So this kind of example will keep on repeating again and again, particularly in this directional derivative and this limits topic. So understand this concept very clearly. Okay. So various forms of the similar function, maybe the powers are different, but same type of question will be asked again and again. So yeah, listen carefully. So you have to find the directional derivative of this function at 0, 0. Okay. So find the directional derivative at 0, 0 in the direction of an arbitrary unit vector. Okay. So first you are considering an unit vector. So now limit h going to 0 f of, so you have at 0, so you have the x value is 0 plus h u1 comma 0 plus h u2 minus f of, here this is the question. So it's specifically they are mentioning at 0, 0. That is why instead of x and y, I am straight away writing what is the values of x and y. Okay. Minus f of 0, 0. The whole divided by h. Okay. Now this is equal to, what is f of 0, 0?
0.
F of 0, 0 is 0. So this term becomes 0. And what about the first term? So you see when x and y coordinates are non-zero, then you get that you have to use this first formula. So this becomes limit h going to 0. Instead of xy, you have to write x squared u1 u2, right? Or if you want to write it step by step, I can add one more step also. F of hu1 hu2 by h, which is limit h going to 0 h squared u1 u2 by h. Right? Fine. Oh, denominator I forgot. By h squared u1 squared plus h squared u2 squared whole divided by h. Now this you can again rewrite as limit h going to 0. Now what is that you can do? H squared u1 u2. So this is actually you can consider as h by 1. So this h actually comes here, right? So then what happens? You will get actually here h cube u1 squared plus u2 squared. So this becomes limit h going to 0, u1, u2 all divided by h into u1 square plus u2 square. Okay. Okay. Now note one thing. So up to this, we have done the usual step. Here, one small thing you have to note. See, given that your vector u is equal to u1 comma u2 is an unit vector. So if this is an unit vector, what can you say about u1 square plus u2 square?
1.
What is the norm of an unit vector? It is the square root of this. So you know that the square root of this is equal to what?
1.
1. So if that is equal to 1, then what is u1 square plus u2 square?
1.
1. Okay. So now this term you can replace with 1. Okay. So this becomes limit h going to 0, u1, u2 by h. Okay. Does this limit exist for a specific value of u1 and u2? Does this limit exist?
No, when h goes
No,
to
no.
0, then it will become infinite. No?
Sorry?
When h goes to 0, it will become infinite. No?
Yeah. So this does not exist. This does not exist. Okay. So this limit does not exist means the directional derivative at 0, 0 in this direction does not exist. Okay. But what about the specific? So here this does not exist when u1 not equal to 0 and u2 not equal to 0. Okay. Now suppose I am considering it in the direction of, maybe I'll write it in different color. Now,
Direction of 0,
Yeah.
0.
yeah.
Direction of 0, 0.
No, not 0, 0. 0, 0 does not make sense, right? Add 0, 0 in the x direction, in the direction of 1, 0. So if it is 1, 0, then what will you get? Limit
0.
h going to 0, f of h, 0 minus f of 0, 0, the whole divided by h. And what is this again? It is, see, when you are putting y as 0, you see the numerator becomes 0. So you will get that here it is again 0. 0 minus 0 by h, limit h goes to 0. So you see already this term is itself 0. So this limit is 0. Okay. Same way, you can find the directional derivative at 0, 0 in the direction of 0, 1. What happens in the direction of 0, 1 again?
0.
Yeah. Limit h going to 0, f of 0, h minus f of 0, 0 by h. Again it is 0 minus 0 by h. So this term itself is 0. So this limit is also 0. So you see at origin, the directional derivative exists only in these two directions. That is in the direction of your x-axis and y-axis. But what are these actually? What are these actually?
The same
Partial
point.
derivatives.
Yeah. So this is the partial derivative with respect to
X,
x. And this is your partial derivative with respect to
Y.
y.
So,
Okay.
So, ma'am, we will come back to this when we discuss continuity and all, right? These kind of examples.
Sorry.
We will come back to these kind of examples when we discuss continuity, right? Like, I wanted to ask
Yeah.
you.
Again, during continuity, this topic will again repeat. Yes.
Yeah, so no, I just wanted to ask, like, even if we define a function like here we defined it at 0, 0, right? So even if we do that, we still the differentiability won't change, right? Like,
First of all, we have to look at continuity. Only when it is continuous at that point, then only we can talk about differentiability, right? Yeah. So during continuity, we can see whether it is continuous at that point or not. So at this point, you see at 0, 0, you see directional derivative did not exist for any unit vector where u1 and u2 both are non-zero. Only in this two direction it existed.
Yes.
Okay, so what happens to the continuity at this point 0, 0, we will discuss after few slides. Okay. Okay. Fine. So the font size is too small, I guess. Okay. So if the directional derivative f of x comma y is equal to x plus xy minus 2y square at the point 2, 3 in the direction is also given is a root 2. Find the value of a. First of all, is the given vector an unit vector?
No.
What is the norm of this vector given? 2 root 2, 2 root 2. 1 by root 2. So this is your v, let us say. Then, so what is your u? Your u is v by norm v. Okay. So your v is 2 root 2 comma 2 root 2 and norm of v is
Underscore.
square root of 16, which is 4, right? So it is actually 4. Is it fine? Okay. Norm v is equal to square root of 2 root 2 whole square plus 2 root 2 whole square. So you will get 8 plus 8. So square root of 16, 4. Okay. So this is the vector you have got. And when you simplify this, you can rewrite it as maybe root 2 comma root 2 by 2. Or simply 1 by root also you can write. 1 by root 2 comma 1 by root 2. See, actually, if you observe that this is actually of the form x comma x. So we know what is the unit vector along y is equal to x. It is 1 by root 2 comma 1 by root 2. So you can straight away write this vector without this computation also, because this unit vector along x comma x, that is y is equal to x, is 1 by root 2 comma 1 by root 2. Right? Okay. Now what is the directional derivative of this function function f along u at the point 2, 3? So you have to consider f of 2 plus h u1. So this is your u1. This, yeah. H times of your u1 is 1 by root 2 and 3 plus h times of u2, which is again 1 by root 2 minus f of 1 by root 2 comma 3 whole divided by h. Limit h going to 0. Okay. So now what is this function given to you? Let us apply it. So limit h going to 0. If we apply this, 2 plus h by root 2 plus 2 plus h by root 2 into 3 plus h by root 2 minus 2 times of 3 plus h by root 2 the whole square. And what is f of 2 comma 3?
2 plus
2
6
plus
plus
6 minus 18,
18.
right? So you get minus 10. Is it correct?
Yes, ma'am.
Okay. So here already there is another minus. So minus into minus, it will become plus 10, right? Here one minus is there and the value itself is minus 10. So this will become plus 10. All right. And then whole divided by h. So now if you have to simplify, so what is that you will get? 2 plus h by root 2 plus 6 plus 3h by root 2 plus 2h by root 2 plus h squared by 2 minus 2 times of 9 plus 6h by root 2 plus x squared by 2 plus 10 again whole divided by. So when you do the simplification, what is that you are getting? So you have to first of all multiply this. So when you multiply, maybe I can write it here. What are the terms you are getting? Minus 18 minus 12h by root 2 plus, minus 2 h squared by 2. So minus h squared simply. So this is by root 2 and here minus h squared. 2 and 2 will get cancelled. So these are the terms you are getting. So now we can simplify easily. So let us first collect all the constant terms. If you are collecting all the constant terms, what is it you are getting?
10. Yeah.
It is 8 minus 18, so minus 10.
Yeah,
Right?
minus 10 is correct.
Fine. And then if you are collecting all the coefficients with h, actually it is h by root 2. So h by root 2, you have 1 plus 3 plus 2 and then here minus 12.
Madam, did you factor plus 10?
Yeah?
Did you factor plus 10? The last digit, yeah.
Yeah,
If
plus
you
10
send
is
the
there. We
calculation
can
down
cancel
below,
out. Yeah, we can
minus
cancel out.
minus 18 minus 12h by root minus h square plus 10.
Minus 10.
Am I making any mistake? What is that you are saying?
It seems that you did factor the h plus h. Wow, 10.
Yeah, this two we can cancel out, right? And the whole divided by h. Okay. Now, what is now you are having, what is this coefficient inside now? 6 minus 12, which is minus 6. So this becomes limit h going to 0 minus 6h by root 2 minus h squared by 2 whole divided by h. So when we simplify, we simply get limit h going to 0 minus 6 by root 2 minus h by 2. Now as h goes to 0, you will just get minus 6 by root 2. And what is given in the question? This is equal to a root 2. They have already given that the directional derivative is equal to a root 2. So
This will become minus 3 root 2. So root 2 will cancel. So a is
Yeah.
equal to minus 3.
yeah. So minus 6 by root 2 is equal to a root 2. So this implies that minus 6 by 2 is equal to a. So your a is minus 3. Okay, so this is your answer for this question. What is the value of a? We have found it to be minus 3. All right. Okay. So the next thing is that we are going to find the limit of sequence of scalar valued functions as well as vector valued functions. So before that, we will quickly recall limit of sequence of real numbers. First of all, a very quick recall. So what are you have done several problems in your math 1 course for this limit of sequence of real numbers. So we'll quickly recall. Let an be a sequence of real numbers. We say that an has a limit a in R if as n increases. If n increases in the sense that we make n go to infinity, right? Then the numbers an come closer and closer to a, right? So we in notation we write limit n goes to infinity, an is equal to a, right? So a sequence is said to be convergent if it converges to some limit. For example, what is the limit of 1 by n? What is the limit of 1 by n?
0.
If n goes to infinity, it becomes 0, right? So
Yeah.
this term becomes, so all this we are considering as n goes to infinity. So this term becomes 0. What about the second one? What about the second one? This is a very familiar one.
E, ma'am.
Yeah, it is a value of e, right? And what about this one? N times of sine 1 by n. Do you remember
Ma'am,
how do you
E-
find the limit of this?
How we are getting E?
Yeah,
How we are getting E? The second one. Second
how
example.
we are doing this, that I'm not going to explain. I guess for E, you will be studying. These formulas are kind of very basic things you should know. I can just tell you that this is the formula. Maybe you can go back and look at this. So you can write it as limit n going to infinity summation I. So this is nothing but I can expand it and write. So 1 plus 1 plus 1 by 2 factorial, 1 by 3 factorial plus etc. Okay. So for the limit of this series you see is E. Okay. It is also the limit of a particular sequence. We will see it next. Okay. So this is something you should know. Okay. And what is the limit? You have definitely done this in your previous course, I guess. Please verify it. Okay. And for this, what is the limit of this? This is a very simple one, right? How do you find the limit of this? You write it as sine of 1 by n and 1 by n.
Oh, 1, ma'am.
Yeah. So you find the limit of this. You use L'Hopital rule and write it as cos 1 by n, right? If you use L'Hopital rule, then this is same as limit n going to infinity cos of 1 by n. And this is nothing but 1. Okay. So the limit of this sequence here is 1. Okay. Fine. And these are all divergent. And there is a particular name for this kind of sequences. What are they called? So the value is like it will go to -1 and then it will come back to 1, again -1, 1. So like this, it will keep on going the movement is to and fro motion. So what is this kind of a sequence called?
Divergent.
Yeah, it is
Oscillating.
divergent.
Oscillatory, yeah.
The specific name is oscillating sequence. Okay, it is oscillating between -1 and 1. Okay, and you know that this is also divergent. This goes to infinity, and this is also going to infinity as n goes to infinity. Okay, so these are some divergent sequences. Okay, so these are common sequences, so you can remember these things, or you should at least know what is the background technique used and remember the answer. Okay, fine. Now limit of sequences in RP. Okay, so you are now considering sequences in RP. So let A and B sequence in RP denote the coordinates of A and tilde as AN1, AN2, ANP. Now we say that AN tilde has a limit A tilde. Okay, if as n increases, the sequence in the ith coordinate has the limit AI. It means what? Limit n goes to infinity, AN tilde is equal to A if limit n goes to infinity, ANI, okay, this is equal to AI for each I. For each I. So you see, each of this should go to this should go to A1, this should go to A2, this should go to AP. Then you can say that AN tilde goes to this A. Okay, this is what is the definition of the limit of a sequence in RP. Okay, fine. So a sequence AN in RP is called convergent if it converges to some limit. So whenever you can find a limit like this, then it is convergent. See, one advantage is that there can be several sequences like this in RP, right? There are, for example, in RP you have P sequences, right? So if you can find that at least one of them is divergent, then you know that the whole sequence AN tilde is divergent. Okay, because for each I you need a limit. If one of them does not have a limit, then you can say AN tilde does not converge. Okay, so what is that I said? If limit n goes to infinity, ANI does not exist for some I. Here for each I told for the limit to exist. For not to exist, it is enough if you show that at least for one I, if it does not exist, then limit n goes to infinity, an tilde, this does not exist. Okay. So we will see with examples the same so you can understand it better. So here you see 1 by n times of sine 1 by n. So what is the limit of 1 by n? We already have seen. This also we have seen. What is the limit of 1 by n?
0.
What is the limit of n sine 1 by n? We just saw above.
1.
1. Right? So this converges to the vector 0, 1 as n goes to infinity. Okay, so as n goes to infinity, this is a sequence in R2. So this sequence in R2 converges to the vector 0, 1 as n goes to infinity. Okay. Now what about the second one? This is again a sequence in R2.
It's
What
div-
about the first term? Is it converging?
No.
No.
So it
So
doesn't.
this is diverging. So if this is diverging, then you can straight away say that this does not, as n goes to infinity, is diverges. Okay, or the limit does not exist. Okay. What about this term here? Cos n by n?
0.
0.
Yeah. For cos n by n, what is the limit?
0.
Cos n is a bounded sequence, right? What it is bounded by which numbers?
-1.
Right? The cos value is bounded by these numbers. So minus 1 by n, cos n by n plus equal to 1 by n. Right? So now by sandwich rule, you know that what is the, now can you tell me what is the limit by sandwich rule?
0.
Both these boundaries, they are tending to which number as n going to infinity?
0.
0. So the limit of this sequence is also 0. Okay. This one we have already seen. What is the limit of this sequence?
E.
Yeah. And what is the limit of this sequence? N times of cos 1 by n. See, cos 1 by n, this is bounded.
That's diverges.
And here, as n goes to infinity, you are having a bounded means you can consider this like some number also. So as n goes to infinity, what happens to this whole sequence then?
Diverges to infinity.
It will go to
Infinity.
infinity, right? This actually diverges. This n will go to infinity. Cos is a bounded function, and then you see that you are multiplying it with n. So this is always bounded, so you can consider it like a number also. Then n goes to infinity means what happens? This is actually a divergent sequence. So there is a big term here. You don't have to even worry about it. You can straight away say what is the limit of this whole sequence. This is in which space? The sequence, full sequence in
R4.
R4. 1, 2, 3, 4 terms are there. So this is in R4. Okay. And you see that this n cos 1 by n is diverging. So this whole sequence, the limit does not exist. Yeah. So what about this one? You can actually verify this. I guess it is explained in one of the videos actually. Did you check that video for this one? I can write it very shortly.
Yeah.
So ln 1 by n, this goes to infinity as n goes to infinity, right? This we know. So then what happens to 1 by ln 1 plus 1, 1 plus n? This goes to 0 as n goes to infinity. Now pi n squared by 1 plus n squared, you can rewrite it as pi times n squared by 1 plus, I can divide the numerator and denominator by n squared. So you will get like this. Now as n goes to infinity, this goes to pi. Right? And then what about the denominator? 1 plus 1 by n, the whole power 2n. Let us rewrite it as 1 plus 1 by n, the whole power n, the whole square. Does this term look familiar to you? I already told you. So you can write the value of E as a limit of two different things which are very commonly used. So limit n goes to infinity, 1 plus 1 by n whole power n is equal to e. This is also something you should know. Okay. So you see that this will go to e and then power 2 as n goes to infinity. Okay. So in the denominator, you have a non-zero value as n goes to infinity. So you can use the quotient rule for limit. So if you are using the quotient rule for limit, now can you tell me what is the limit of this sequence given to you here? What is
5
the
by
limit of this value?
5 by e square.
Plus 5 by e squared, which is 5 by e squared, right? Okay.
Ma'am, is sine also bounded function?
Yes, sine, cos, both are bounded functions. Okay. Fine. So now let us look at limit of scalar value multivariable functions. Okay.
Ma'am, total how many weeks are there in Maths 2?
One more week is left. That's all.
Okay.
Okay. So
I
we
guess
are in week.
11,
Yeah.
11, right? 11 total 11 weeks, no?
Oh, sorry. Yeah. Week 10 and 11. Yeah. 2 more weeks left. Sorry. Yeah. Okay. So limit of a scalar value multivariable function. If there exists, sorry, if there exists some scalar some real number L such that f of x1, x2, xn. Okay, this we usually denote with x till, right? Approaches L as x1, x2, xn approaches a1, a2, an. This we denote by a till, right? So it means what? Limit this x till going to a till f of x till, we call it L. Okay, so this is the limit of this scalar valued multivariable function. So you see the limit is now a number. Even though you have a function of n variables, still the limit of this function is a number here. Okay, if there is no such number, then we say that the limit at this particular point, particular vector does not exist. Okay, so here you see that limit x going to x tilde going to a tilde. So here, for example, they are considering only one particular coordinates. All these things they are considering only for one particular I value. Okay, so maybe it can be x1 power k or x2 power k or anything. Okay, so let us say your x tilde is equal to x1 comma x2. Okay, then what happens to your, just a minute. So what happens to your limit x1, x2 going to a1, a2. Let us say, for example, x1 power k. What is the answer? So here, yeah,
A1 power
a1
k
power
is
k. Right? Now, suppose your number k is non-negative, this is the answer. Suppose k is negative, again, the answer is going to be the same only, right? It's not going to change anything. So you have limit x still going. So the answer is going to be simply again, you have ai power k only. Nothing is going to change if their power is changed. Okay, provided ai is not 0. Remember, when for this limit to exist, you should have ai to be non-zero. Okay, otherwise it does not make sense. Okay, so here powers, exponential powers. So we saw generally power functions, exponential functions, logarithmic, or any trigonometric functions. All these are continuous functions. So we know that you can apply the limit very easily. So what is the limit of this one?
E raised to a
E power
AI
ai. And here what is the limit?
log AI E raised to
Again,
AI.
ai. Right? See here, logarithm is defined only for positive values. So again, this condition is important here. Otherwise, it will not make sense again. Okay. And what about this one?
Sin AI.
Sin AI. And here, see here the domain is particularly mentioned because what happens at pi by 2? What is the value of tan at pi by 2 or minus pi by 2?
Multiples.
It's undefined, ma'am.
Yeah.
Yeah, it is not defined, right? So you are considering AI only where the function is defined. Okay. So what is the answer in this case?
Tan AI.
Tan AI. Okay. Fine. So what are the rules we should follow for the scalar valued multivariable function? It is again the same, just like in the case of the limits for just the scalar functions. So here you see that the sum and the scalar multiple can be splitted, and also the product you can split provided both the limits exist. First of all, both the limits should exist, then only you can apply all this rule. Okay. And for the quotient rule to be applied, you should know that the denominator limit is non-zero, right? And for composition, see, for example, I can tell you a very easy example. Note that here g is a function of one variable and f is a scalar valued multivariable function. Okay. So for example, I'm writing f of x comma y is equal to some x squared plus 2 times of xy minus 3 or something like this I'm saying. Okay. Or plus 3 or minus whatever. So now you see that what is limit x comma y going to 1 comma 0 of f of x comma y. What is the limit? Can you tell?
1 minus 3.
It is
minus 2.
minus
Minus 2.
right? Oh, now let us say you have another. So g is a one variable function. So let us say your g of x is equal to e power minus x. Okay. Now what is, you remember here this f only is applied here. Limit x goes to minus 2 g of x. What is the answer?
E raised to 2.
E power
2.
2 e square, right? Okay. Now what is g composition f of x comma y?
It will be same like E
E
raised.
square.
No, g composition f of x comma y. I have not applied limited.
Okay. Then E raised to
E
that
power minus
x square
x squared minus
Minus
2xy
2xy
plus
plus
3.
3.
Right? Now, if I am applying limit x comma y going to your a tilde, which is 1 comma 0. G composition f of x comma y. What is the answer you will get? Minus e power minus 1. This will become 0 and plus 3. So it will become
E
e
square.
square. So you see that limit x goes to f g of x is equal to L, and the same is the limit of limit x tilde going to a tilde g composition f of x tilde. Okay. So you see what are the values which are equal? This one and this one. So you see you have got the equality here. Okay. And the sandwich principle is very much same like the one you have used previously. Okay. So if your f of x tilde less equal to h of x tilde less equal to g of x tilde, then limit x goes to a f of x tilde is equal to L, where here I guess it is h. Okay. It is h here. So if you know that the limit of this boundary functions are L, then you know that the function which is sandwiched in between f and g, that is also L. Okay. So some people call the same principle as squeezing principle or something like that, squeezing theorem and all. Okay, I guess you are very familiar with this from your Math 1 course.
Ma'am.
Okay. So limit of a function at a point along a curve.
Ma'am, can I ask?
Yeah.
Yeah. So when we find this here, it's f and g. So when it's just intuition, or like is there a method for taking those?
Which one, ma?
Like if when we find this fx and gx, like those two upper and lower functions, like
This one.
yeah.
See, for example, what is f of x tilde? F of x tilde, it is going to look something like this. It is going to be something like this. It is a scalar valued function. So whatever function you are having here, okay, so that function, it should obey some rules like this. Okay.
Okay.
So f of x till whatever function it is here, that should be less than or equal to this function, and this is less than or equal to this function. So each of them, they are all functions. And for any given values of x and y, they all should satisfy that the values are less than or equal to the other values.
Okay. Now,
Okay.
like when here the function is given, so in general, if we are like calculating the limit and when we apply sandwich principle, we
Hmm.
have to come up with these functions, right? Like
Yeah.
lower bound and upper.
Yeah.
So,
Yeah.
so for that, like, is it just intuition or like, or there is a method of picking those? Like,
See, once a function is given to you and you are finding the limits, first of all, if you have a feeling that it is bounded, then most probably it is easier to found this bounds. Okay,
okay,
first of
like,
all,
yeah,
under which condition you have to use sandwich principle? Two things. First of all, you have a feeling that it is bounded, and also it is not straightforward to find
yeah,
the limit
no,
directly. If you
yeah,
if you can find the limit directly, you don't have to do all this sandwich and all. So when both these are conditions are there, then you try to do the sandwich by finding what is f and g. Okay.
okay, okay,
And f and g, of course, you should use your intuition to find what can be the f and g. Okay. Usually it is something very similar, or something only plus or minus difference is there, or something like that is there for finding this f and g. So it should not be very complicated for familiar functions. Mostly it is easier to find for the familiar examples. If you try some examples, then you can find it easily whether you have to use sandwich principle and how to find f and g. Okay.
okay, okay, thank you.
Fine. Okay, so limit of a function at a point along a curve. Okay, fine. So for finding, mainly not finding, for disproving that some function does not have a limit for scalar valued functions. What is that you do? There is one technique which you do for saying that limit of a function does not exist for scalar valued functions. So what are that? So for example, f of simple functions, if I'm saying, so let us say you are having a function f of x. Okay. So when do you say that this f of x does not have a limit?
We take two curves and like when
So using a sequence, I'm asking the question using a sequence.
like when they diverge, like just what we said, one diverges and one converges like this.
Yeah. So you see limit x and limit x goes to a, f of x. Okay. So this you can say it exists if for every sequence a n, f of a n converges to L. That you can say, or the other way around, if you can find a sequence a n converging to a for which f of a n does not converge, then you can say this sequence also does, this function also does not converge, right? The same concept is what we are going to use here. I'm going to explain it now. Okay. So let me explain it step by step. So consider this function here. Okay. So here instead of sequence, yeah, you can use sequences also, and you can also use different curves. So using curves is something very common for this kind of multivariable functions. Okay, fine. So let us see what are the different curves. Here we are in R2, x comma y, two variables are there. So we are in R2. Okay, in R2 you can have you can consider any parabolas or lines or just the x-axis, y-axis, anything you can consider. Okay, all these are curves. Okay, so now let us consider this function limit x still going to x comma 0 comma 0. So x comma y is going to 0 comma 0 for this function. Now does this limit exist or not? How can we find? For this, instead of directly finding the limit, what is that we can do? We can find what happens to the limit along some specific curve. For example, what happens to this curve, to this function along x-axis? Along x-axis, what is your value of y?
0.
0.
If y is 0, then what happens to this term given to you?
x3 by
X
Already you
cube
know
by
y is 0, so I'm not writing
x
y
power
here.
4
Only
1 by x
x cube
by
by
x power
by
4
square 4.
x power 4. And this is,
1 by
1 by
x.
x.
and does this limit exist?
No.
So So if you can see that in one direction at least, if this limit does not exist, then what can you say? This limit does not
not
exist
not
in
exist.
general. Okay, but be careful. Sometimes what happens, the direction in which you choose, that direction it may exist. In some other direction, it may not exist. For example, what happens along y-axis? Let's see. What happens along y-axis?
It will become minus
0.
0.
So here your y value is fixed. Oh, sorry, x value is fixed. Only y goes to 0. So x is 0. So the whole term becomes 0.
0.
So here you see 0 minus 0 by 0 plus y squared whole square, which is 0. So you see in this direction it is particularly existing. And what happens along the line y is equal to x, for example? In that case, what will happen?
0.
Yeah. So if you are putting y equal to x, you get x cube minus again x cube by here x squared 2x squared the whole square. Again, it is 0. So you see, if you are starting with this, then you see that, okay, you will think that all the limits exist, may be existing, but be careful. You have to try with various different directions. To mainly, this method is used only when you are going to prove that the limit does not exist. Otherwise, you don't use this method. Okay. So using different curves for finding the limits, you use only to prove that the limit does not exist. Okay, fine. Because there are infinite number of curves, you cannot prove in that the limit exists in all the directions so that the limit exists. Okay, only the counterpart you use, that the limit does not exist. All right. Okay. Yeah.
Yeah. I have a question. Like, so what does this mean? Like, you have number of lot of curves, like you said. So along this curve, along that curve, and this limit exists or does not. What does this mean graphically? Or this function is
See,
some curve, right?
I
This
guess you have
function.
seen step functions, right? See, in the case of scalar valued functions, you only have two directions: left limit, right limit, right?
Okay.
Right. So, for example, if you are having some step functions where you have a jump discontinuity, for example, this is 1, and you are having a function like this. Okay, and here it is like this. Okay. Now you are defined that f of x is equal to, let us say this is 1 and this is 2. Okay, x, sorry, it is f of x is just 1 if x is less equal to 1, and it is 2 if x is strictly greater than 1. Okay, now what is the limit as x going to 1 from left? From the left side, if you are coming, what is the limit?
1.
1. And what is the limit of the same function when you are coming from right?
2.
That is infinity, no?
Here you see this
2.
point, it is not defined. At 1, this point, it is not defined. It is, so this does not exist.
Can we say it is infinite?
Yeah?
Can we say it is
From
infinite?
No.
Can we say?
Infinite.
No. This is not infinite. It just does not exist. Infinite means it will be, the curve will be just going somewhere up.
Okay.
Right? It
no,
is
it's
not going
approaching
like
2, right?
Ma'am, and 1 plus it will equal to 2. That's
2.
what
Yeah, it's approaching to 2, right? But it is not 2 at 1.
Yeah,
There
sorry.
is a
In this,
discontinuity.
in this example, it is approaching, the limit is approaching 2, but the limits are not equal, right? This is also applicable here. So when
The
the
limits are
both the
not
limits,
equal.
left and right
There is a
hand limit,
discontinuity.
let me just complete it. So when both left and right hand limit exist and are not equal, you know that the limit as x goes to 1 does not exist, right? So
Yes.
both the limits should be equal for the limit to exist, right?
Yes.
Yeah. So you see that limit x goes to 1, f of x does not exist. So the same concept you can use here. Sometimes what happens, all the limits will be existing, but they are not equal. So the same concept you can use here. So along some curve, you see that the value is different. Along some other curve, the value is different. I guess there are some tutorial videos where you get different values for different curves. I don't remember exactly the
Also
example,
selecting
but
the
for
curves is intuition, right? Like when you want to disprove, like when we want to say there is no like limit exists, we have to use our intuition to select those curves, right?
actually it is just by trial only we have to see, because what happens, it is very easy to visualize in the case of R2, but in this kind of functions it is not easy to visualize. That is why here you just have to do trial and error only. So we usually use only some basic functions. Very rarely we go to some parabolas and all. In general, we use x-axis, y-axis, or the line y is equal to mx also we use. Sometimes we use some parabolas. These are the basic curves you use for verifying this condition.
One of the examples we had to use like a parabola.
Sorry.
I think one of the problems we had to use like a parabola. I don't remember the problem. Like,
Yeah. There is one example I have. I have next where I have used parabola. So this is one example where the left hand limit and right hand limit are not coinciding. Suppose I'm defining another function. Let us say f of x is equal to 1 by x. Okay, 1 by x for, let us say, x is greater than 0. Okay, and let us say for x less than or equal to 0, it is simply 0. Okay, let us say there is a function like this. Now, how is the curve looking like? So here you see from the left side all the way around, here it is like this up to this point, and here it is just going up, right? When it comes closer to 0, it is going towards infinity actually. So in this case, for example, there are two cases where we can say the limit does not exist. So I'm telling the other case. So limit x goes to 0 minus f of x. What is this limit? From the left, what is the limit?
0.
0. But what happens to limit x goes to 0 plus f of x?
Infinity.
It does not exist, right?
Yeah.
So in this case, you see that in one side it is existing, in the other side it is not existing. So you can in general say that limit x goes to 0, f of x does not exist. The same concept here we can use. There are two possible cases. One is that in some curve, along some curve, it does not exist like it happened here. And sometimes it happens that the limits in different curves exist, but they are not equal. So in either case, you can say that the limit of this function does not exist. Okay, am I clear?
If the limit does not exist, can we say the function is undefined at that point?
Not exactly, because for example, here you see what is f of 1 is very clearly defined. Just the limit is not existing at that point. Okay.
Even this one
Fine.
x equal to 0, it's defined like 0 here.
What
Okay.
happened?
And even in this problem, x equal to 0, it's defined like defined as 0.
Yeah. So you cannot say that in general the function is not defined. The limit does not exist is different from the function is not defined. Okay.
Okay. Thanks.
Yeah. Any other doubts? Okay. Let us continue then. The limit of f at a till exists and equals L precisely when for every curve C in the domain D passing through A, the limit of f at A along C exists and equals L. Okay, but this is what is kind of the sequence thing we are using. So limit x goes to a, f of x exists if for every sequence n converging to a, f of n converges to some limit, that will be the limit of this sequence also. So instead of sequence, here we are having a curve, and usually this we are not going to use for finding the limit of the function, but to show the limit does not exist, we are going to use this. Okay, so let us do some examples so that we will understand it better. Consider this example here, limit x comma y going to 0 comma 0, x squared minus y squared by x squared plus y squared. Now what happens along x-axis? Usually we are starting with x-axis, y-axis, y equal to x and so on. Okay, so along x-axis, what is your y value? 0. So what is x comma y going to 0 comma 0? What is the function?
X square by x square. That's
It is
one.
going to be x squared by x squared, which is
One.
1.
1. Okay. Now along y-axis. Here x is 0. Now what is the value?
Minus one.
Minus 1.
Yeah. So you see it is minus y squared by y squared. So it is minus 1. So you see both the limit exists, but they are not equal. So now, does this limit exist?
No.
This does not exist. Okay, fine. Let us do the next question. Limit x comma y going to 0 comma 0, xy by x squared plus y squared. Again, what happens along x-axis?
X equals to 0, then
0.
0.
Okay, limit x still going to 0 comma 0. It is 0 by x squared plus
0.
0, which is 0 actually. Okay.
Even along y-axis also it will be
Yeah,
0.
along y-axis, your x is 0, so the same will happen. Limit x comma y going to 0 comma 0 is simply 0 by 0 plus y squared, which is 0. Okay. Now, in this case, we have to look for the next option. What happens along y is equal to x? Let us check. Along y
Right.
is equal to x. What happens along y is equal to x? Limit x goes to 0. You have to substitute y with x. So x squared by
By
2x
x
squared, which is
1
1
by
by
2.
2. So you see that this is not equal to the limit of the other values.
Does
So
not
does
exist
this
again.
limit exist then?
No. DNA.
Okay. So this is not equal to these values here. That is why the limit does not exist. Okay. Now let us look at the next example.
This way we could have, madam, we could have tried 0, 1 and 1, 0 also that way, no?
Sorry, 0, 1 and?
I mean, any other number besides just x, the line itself, we could have taken some parable also, you know?
Yeah, we are going to do it for this example.
Okay.
Okay, let us do it for this example. So what happens for this example along x is equal to 0, along y is equal to 0. So instead of
0.
yeah, so along x-axis
Axis,
and y-axis, what is happening along x-axis and y-axis?
0.
0.
The limit is going to be 0, right? Limit x comma y is simply, it is 0. I will write 0. Okay, fine. Now let us consider what happens along
The line.
any line. Y is equal to mx if I'm taking. Along y is equal to mx, now what happens?
Mx square. Oh,
M
mx
square
cube
x
X
cube
cube.
by
divided by
x
mx
square
square
plus
X square x square.
mx square.
m power 4 x power 4.
Yeah.
So this is m square x by 1 plus m square x square, right? Limit x goes to 0. What happens? What is the limit again?
0, no?
0, right? So now we are done with the usual things. So we have to try with the next option then. So along x is equal to y square.
Yeah.
Now what happens? Limit x goes to 0.
X,
Y
y cube.
squared can replace
Yeah.
x. So x square plus x square, which is 1 by
By
2.
2.
So now you see that this
Left
is
side is
what
not equal to
the
right.
other limits.
Ah.
Yeah,
So that bit does not exist again.
it does not exist. Why?
Because left hand side is not equal to the right hand side. No?
Yeah, this limit does not exist. Yeah.
This is along which curve? X equal to y square, right?
Yeah, x is equal to y square.
So then what will be the numerator? So
What
y
will be
cube,
the
right? Numerator x.
instead
If
of
you
y squared, I'm going to put x. So
oh,
x
okay.
square.
Okay.
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 So So these are the basic curves you should try for finding, for verifying that the limit does not exist. Okay. So you can try with different parabolas depending on your question. What is your question? Depending on that, you can try with different parabolas. Okay. So next thing is that limit of a vector valued function at a point. Okay. So far we have seen only limit of scalar valued function. The next concept is limit of a vector valued function. Now let let f from D to Rm be a vector valued multivariable function. Here domain is Rk and A tilde be a point such that there exists a sequence in D which converges to A tilde. Okay. So now what is limit x tilde going to A tilde fi of x? So f is now it is having k functions f1, f2, fk. Okay. So each of your functions fi, if they have a limit, then only you have a limit for the function f. Okay. Here you are having a vector valued function. So f is not just a number, it is a vector function. Okay. So here, for example, you see this is your f of x tilde, or what to say, I don't know. Maybe I'll write it as f1, f2, f3. That is better. So this is your f1, this is your f2, this is your f3. Okay. So this is your function. So you have to check whether the limit of each of this function exists, so that you know the limit of the whole function exists. Okay. If one of the limit does not exist, then you can say that the limit of this full vector valued function does not exist. Now what happens to limit x comma y going to 1 comma 2 f1 of x comma y 1 comma 2? If you substitute, what is the answer you are getting?
2.
2 plus 8.
8, yeah.
10. Right? So as x tilde goes to 1 comma 2, your f1 goes to 10. Now what happens to your f2?
E square.
It is simply e square. So your f2 goes to e square. What about your f3?
0.
You have to put 1 minus 1. So the numerator is becoming 0. So this f3 goes to 0. Right? So what is the limit of then this function? Limit x tilde going to 1 comma 2, f1, f2, f3,
10
1
e
comma
square.
e square, comma 0. So now the limit is not just a scalar value, it is a vector. Okay, the limit is now a vector. Okay, fine.
So
Now
it's so simple, like you just need to input the values of x and y
yeah, it
and
is
find
quite
out
simple
the.
only. Yeah.
Okay.
Okay.
So how the question will be framed, madam, if I may ask
How
you?
to?
How the question will be framed? So here these three vectors, these things will be given and will be asked to
Anyway,
find.
maybe you will be given something like this, and several options for the limits are given. Anyway,
Okay. Okay. Okay.
okay,
Or
here
we need to
several
find it out.
possibilities.
Okay. Okay. Okay.
Ma'am, if f1 is 10 and f2, f3 are 0, then what will be?
Then you put 0, 0 here.
Then it will be exist or not?
See, if it is 0, of course it exists. But if the sum function, the limit does not exist, then it is difficult. For example, suppose you have something like, I don't know, maybe 1 by y minus 2x. Suppose you are having. So in that case, for this function, does the limit exist?
No, ma'am.
Does the limit exist for this function as x goes to 1 comma 2?
No.
No.
So if such a function exists, then the whole function does not have a limit.
Okay, ma'am. If
Okay.
any one of does
Yeah,
not
if
exist,
any one of the limit does not exist, then the whole function will not have a limit.
Here
Okay.
the rule does not apply, madam, when the limits are different.
It does not matter because each f1, f2, f3, they are different components, different coordinates here.
Okay.
So different coordinates will have different limits.
Had it been just one, but we are using different points, then if they are not equal, then that limit does not exist, right?
So you are talking about different curves you are using,
Yeah,
right?
yeah.
Okay. Fine. So the next question here is sin xy by xy. So this is something very common. So what is limit theta going to 0? Sin theta by theta? This is some very
One.
familiar limit. Yeah?
One.
1. Right? So in that case, what is the limit of this function here?
1.
It is
1.
1. And what about this function? Does it
0.
look familiar?
Is it not 0?
This is a
Yeah,
function, right?
this one limit does not exist,
Does
right?
not exist.
Yeah. So then what happens to this function?
Does not exist.
Yeah. So you can say that this limit does not exist. So the whole limit, this does not exist. Okay? Fine. Okay. So in the next concept, we are going to continuity of a function. What is continuity of a function? The exact same definition, just like you have used in the scalar valued functions. So they scalar valued one variable functions. So limit x tilde, I guess it is written here. Limit x tilde going to a tilde, f of x is equal to f of a tilde. Then you call that this function f of x is continuous at a. Okay. So it means whenever you are able to substitute the value of a to this function and you get the value of the function, so you get that the function is continuous at that point. Okay. So limit x tilde going to a tilde, f of x tilde is equal to f of a tilde. If this condition is satisfied, then you say that this function f of x tilde is continuous at the point a.
So
Okay.
what is domain here?
The domain is, of course, x tilde means it is in some vector, right? Rn, I guess. Yeah, Rn. Okay, vector valued functions.
Okay.
Sorry, multivariable functions.
Mhm.
Okay, these are multivariable functions and scalar valued. Multivariable scalar valued functions. You see the codomain is R and the domain is Rn. So scalar valued multivariable functions.
So x tilde is basically those elements of domain, is it?
Yeah,
X tilde are the elements of the domain.
x tilde is x1, x2, xn. And a1, a2, an is again an element of the domain.
So both of them are the elements of the domain, is it?
Yes, yes.
Okay.
Okay, fine. But f of a1, a2, an, this is a scalar.
Okay.
Okay, fine. So for continuity of functions, now consider this function g of x comma y, where you are given for x comma y not equal to 0, it is given like this, and for 0, it is 0. Okay. Now let us look at the continuity of this function at 0. Okay. Continuity at 0. So let us first consider a non-zero number and see what happens to the continuity at non-zero values. It is any non-zero number, any non-zero vector.
0, 1.
Sorry.
Let's take 0, 1.
I'm first doing, I can directly do it for arbitrary values. Okay. And then
Okay.
if you want specifically, I can do it for one particular value.
Okay. Okay.
But it is easier to see even for arbitrary case itself.
Sure.
Okay. Now, g of x comma y, it is in the form of a quotient function. Okay. So when can we say this limit of this kind of a function exists? If both the limit of the numerator and the denominator exist and the denominator limit is non-zero. If that is there, then we know that the limit of the whole function exists, right? So we are going to use that. So let us denote the numerator by f and the denominator by h, let us say. Now what is limit x comma y going to some a1 comma a2 f of x comma y? They are just some polynomial functions, right? So what is the answer?
A1 cube minus
a1 cube minus
A2
a2
square
square a1.
A1.
You know that this limit exists. And what about limit x comma y going to a1 comma a2 h of x comma y?
A1. square plus A2
a1 square plus a2 square,
whole square.
the whole square. And we have assumed that your a1, a2 is non-zero. So at least one of them is non-zero. So in that case, will this also be non-zero?
Yes.
So you see the denominator limit also exists and it is non-zero. So in that case, you know that the limit of this function g of x comma y as x tilde going to a tilde, it is simply g of a1, a2, right? So this limit exists. So it means what? G of x comma y is continuous for all not equal to 0. Okay. So for all non-zero values, the function is continuous. Now let us look at the case when your a value is 0. Now your a is 0. Now what happens to the continuity? Okay, what happens to the continuity when it is 0, 0? Have
Goes
you
to
already checked what is the limit of this function as x goes to 0, 0?
yes.
Did we do? I guess we did it somewhere. This one only, right? This is the function, right? Someone also asked whether we are looking at the continuity of this, right? So you know that the limit of this
Does not exist.
x comma y going to 0 comma 0, g of x comma y, this does not exist. Okay, it means what? Your g of x comma y is not continuous at 0 comma 0. Usually you see the discontinuity happens in many piecewise functions. So for discontinuous functions, you consider many piecewise functions, right? So and where the pieces vary, that point, usually the discontinuity happens. So you can guess where the discontinuity happens. So here at this point 0 comma 0, you have a discontinuity. Okay, fine. So okay, so someone asked in the previous class, just like for finding partial derivative, there is a formula where we use the limits and there is a formula where you directly use the formula of derivatives. Same way, do we have something for directional derivatives, you asked, right? So I told you when we are going to study gradient, you will get a formula. So that is what I'm going to do now. So I don't want to do the whole problem of finding the directional derivative because I just did it already. So I'm going to use the same. In the very beginning, we found the directional derivatives. So from there, I want to come to this topic. Okay. Okay. So I will come from here itself. So here, maybe some other different colors. Yeah. What is the partial derivative of f with respect to x?
1.
What is the partial derivative of f with respect to y?
Again one.
Okay.
1.
1, right? So you consider fx comma fy, okay, which is 1 comma 1, and then whatever is the unit vector u1, u2. What is the dot product of them?
U1 plus U2.
u1 plus u2. Okay, did you see that it is matching with your directional derivative?
Yeah.
Yes.
It is not coincidental. So let us look at the other example as well.
And provided they were unit vectors, right?
Yeah.
Provided they were unit vectors.
Why I am multiplying with unit vectors?
No, I'm saying provided u1, u2 were the unit vectors there. We were not supposed to take a norm of this and divide it by that and all that.
I have already assumed that the vector u is a unit vector.
Ha,
See?
ha, 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 ha. Correct.
Okay. So here now what is your function? This is your function. Now what is your fx?
Y plus Z.
Y plus z. And fy?
Z plus X.
Z plus x. Is it z? Yeah. X plus z. and z is
X plus Y.
y plus
X.
x,
X.
right? So you see again here fx, fy, fz dot product with u1,
U1, U2, U3.
u2, u3 is nothing but this expression. Agree?
Yeah.
Right? Y plus z, z plus x, y plus x. Right?
Hmm.
The same you can check here also. What is fx? Cos xy into,
Y.
and what is fy?
Y.
Again
X,
cos xy
XY into
Into
X.
X.
x. Now what is fx comma fy dot product with u1 u2? You get the same answer,
Correct.
right? So this is a
Yes.
shortcut for finding the directional derivative, and there is a specific name for whatever is this vector here. Okay, that is called the gradient function. Okay, so that is what we are going to see here. Directional derivative in terms of gradient. So what is the gradient vector of a gradient vector or gradient function? So gradient vector is nothing but, suppose you have f of x1, x2, xn, it is a function. Okay, and the partial derivatives of this function f exist at a tilde. Then the gradient vector of f at a tilde is nothing but the partial derivatives with respect to each of these variables. Okay, that is your gradient function. So this you call as del f of a tilde. Okay, del f of a tilde is your gradient function. Okay, fine. So if you are evaluating at a specific value, it is a tilde, or if you are putting in a general for arbitrary xy, x1, x2, xn, it is del f of x tilde. Okay, so this is the gradient vector, and it is the gradient function. Okay, so this example also we just did f of x comma y we just did. So we can skip this example. Okay, let's do this one. What is del f of x comma y comma z?
2X, 2Y,
2x
2Z.
comma 2y. Don't forget the comma 2z.
Yeah.
Okay, so this is your gradient. So what is the directional derivative? Let's say u is u1, u2, u3. Do I have any specific vector for this example? Let me just check for a minute. So in that case, du of f is simply del f dot u, which is 2x u1 plus 2y u1 plus 2z u1. Okay,
U2, U3.
Madam, all U1 or
oh,
U2?
sorry, u2, u3.
Hmm.
Okay, fine. So for example, suppose if you want to find the gradient vector at some value, just I'm randomly writing 1 minus 3. Now what is the gradient vector?
2, comma,
2
4,
comma
comma,
4
4,
comma
comma, minus 6.
That's all.
And it can be also given that at a point something, right?
Sorry?
We would be given as U also.
Yeah, you can put some u value, find the directional derivative in some specific direction. For example, 1 comma 2 comma minus 2. So
Okay.
this is this a unit vector?
No.
No.
No. So if you are converting into unit vector, then what will you get?
1
1 by 3.
1 by 3,
1, 2 minus
2
2.
by
2 by
3,
2 by 3.
minus
2
2
by
by
3.
3. Okay. So what is your directional derivative at this point along this vector u?
2
It
by
is
3.
2 comma 4 comma minus 6 dot 1
by
3,
3, 2 by 3, and minus 2 by 3.
which is
2 by
2
3,
plus 8
8.
plus 12
Correct.
by 3,
By 3.
Correct.
which is 22 by 3. All right. Okay. So next you have a function f of x comma y is equal to xy by x squared plus y squared. So for at x comma y not equal to 0, this is defined. So if you want to find the values at 0 also, you need the definition. Otherwise, you cannot define the partial derivatives at 0. So you have to define it as 0. Then only you can find the partial derivative at 0. Otherwise, only at non-zero values, you can define the partial derivative. Okay. Now, what is your fx? The partial derivative. With respect to x, it is?
Y by 2x.
You have to use u by v method, right?
Ah,
Y
Okay.
into x square.
What is the answer?
Y into x square plus y square.
So this is your u, this is your v. With respect to x, you have to do. So denominator
X
is x
cube.
squared plus y squared, the whole square.
Whole square
Yeah.
And then v is x
X
squared
cube
plus y squared
into y.
x minus xy into 2x. Right? Here 0. So it is x cube plus xy squared minus
Minus x square
squared y
2x. Yeah, 2x.
whole divided by x squared plus y squared whole square. So this is when your x comma y not equal to 0 comma 0. Okay, and here x comma y equal to 0 comma 0. Okay, the same here also.
Isn't it x square plus y square into y?
Sorry, what's the question?
X square plus y square into y, right? Like,
Did I make any mistake? Minus 2x squared y by x squared plus y. Everything is fine, right? What's the problem?
fx equal to x square plus y square into y.
into y. V u dash.
Okay, fine. Here it is y. Yeah, correct. So it means you will have x squared y.
Y cube.
Yeah, thank you. So this is x squared y plus y cube. So actually this reduces to minus x squared y, right? When you add these two terms.
Yes.
So simply y cube minus x squared y. So this is your fx. Same way, what is your fy?
X cube minus y square x.
Fy is equal to
X cube
x cube minus
y square x.
y square x, exactly. So x squared plus y squared, the whole square, and 0. When xy not equal to 0, 0, and xy equal to 0. Okay. So what is your gradient vector then?
Y cube
Y
minus
cube
x.
minus x squared y by x squared plus y squared whole square, comma, x cube minus y squared x by x squared plus y squared whole square, when x comma y not equal to 0, 0, and 0 if x comma y equal to 0, 0. Sorry, 0 comma 0. Okay, so this is your gradient function. So the same properties which you have derivative for derivative, the same is applicable for gradient as well. Okay, nothing new here. The linearity property, product rule, quotient rule, everything is very similar to the derivative properties. Okay, fine. So the directional derivative using gradient, this is an important formula to find the directional derivative. Okay, so here is one example. Find the directional derivative of the function f from R2 to R such that f of x comma y is equal to 3x squared minus 2xy in the direction of the vector 3 comma 4. So first of all, what is that we need to do? We have to find the gradient function. So what is the gradient function?
6x
Come
minus 2y,
Minus 2y.
comma,
minus 2x.
okay. And what is the unit vector u?
3,
1 by 5, 3 by 5, 4 by 5.
3 by 5, 4 by 5. Okay. Now what is your directional derivative du of x comma duf of x comma y. You have to do the dot product. So what is that you will get? 18x minus 6y
by 5.
minus 8x whole divided by 5. What is the answer? 10x minus 6y whole divided by 5. So find the directional derivative. I guess here divided by 5 is missing, right?
Yes, ma'am.
Why is it so?
Then only this will be a correct option. Okay, fine. The temperature at a point x comma y comma z is given by this function, where T is measured in degrees Celsius. Okay, and x, y, z are measured in meters. If the rate of change of temperature at 2 comma minus 1 comma 0 in the direction of this vector is given like this, find the approximate value of k. So it is a very simple problem of finding the directional derivative only. So what is that you will do first? Find the gradient function f. What is your gradient function? What is your gradient function? What is the
E
first
power
thing?
x.
Minus 2x into 10 into this function. So you can straight away write minus 20 e power
Power
Minus x
minus
square
x
plus y. Plus y
plus
square
y
minus
square
4x.
minus 4x.
and here 20,
Three.
sorry, 20y. Here also x is missing, right? You have minus 2x. So minus
Yes.
20x.
X.
Same way here 20y.
Y. 20y
20y into e power
minus x square plus y square minus 4
Alright.
z square.
and then here you have minus 8z.
4.
So you
minus
have
4z
minus
into 10.
80. Yeah. So this is your gradient function. Now gradient function at which value, which
2,
point?
1, minus 1 and 0.
Yeah. So it
We'll
is
do a dot product.
z is 0, your y is minus 1 and x is 2. So what is that you will get? Minus
Minus 20, 40.
40.
E raised to power
E power
minus
Maybe we
4.
can keep the e power outside because it is
Correct.
common for everything.
Correct.
E power minus 4
Oh,
plus 1 minus 0. Okay. Comma here 20
Minus
and y
20.
value is minus 1. So minus 20. And z
0.
value is. So the vector is e power minus 3 times of minus 40 minus 20.
0.
Okay. Now what is the next thing you have to find? You have to find what is the unit vector.
Yeah.
So it is 1 by
1 by
Root 3.
root 3.
minus 1
Minus
by
1 by
root 3
root 3.
and 1
And
by
1
root.
by root 3.
Now what is your directional derivative?
Dot product of these two.
Yeah. So when you do the dot product, what will you get?
Minus 40 by root 3.
Plus 20 by root
By
3
root 3.
into
E raised to power minus 3. Yeah.
So minus 20 by root 3 e power minus 3. Okay. So here you see
K
that
is
you have
minus
to
20.
equate it with k e power minus 3 by root 3. So what is your k
K is
then?
minus 20.
20 minus
That's
20.
all. Okay. Quite straightforward.
Yeah.
Okay. I guess one last question.
For today's session or for this activity?
For this week as well as the session.
Okay.
Okay. Let f from R2 to R be given by f of x comma y. So you have to find the directional derivative along this vector u and along this vector v. They have already specified that they are unit vectors. Okay. So first of all, what is the gradient function?
fx
Yeah,
2x plus
not plus, minus
min-
2.
minus
Minus
2y minus 2y
2y, comma 2y
y
minus
minus 2x.
2x. Okay, fine. So this is your gradient function.
And
At
we've been given unit vectors already.
Yeah, you have to find it at 1, comma 2 as well as 2, comma 1. So at 1, comma 2, what is the value?
2
2 minus 4.
minus 4. Yeah.
So minus 2. Minus 2, comma 4 minus 2 is
2.
And what is the gradient function vector at 2, comma 1?
Is 4
2,
minus
comma
2.
minus 2, right? 4 minus 2 is 1. Sorry, minus 2 is 2. And then
Minus
2
2.
minus 4 is minus 2.
Correct.
Is it correct? Okay.
Correct.
Okay. And now du of f at 1, comma 2. What is that?
Is minus 2 in minus 2 2
Minus 2, comma
multiplied
2
by
dot 1 by
1
root
by
2,
2,
comma minus 1 by root 2.
Correct.
Which is minus 2 minus 2 by root 2. So
0 minus 4 by root 2,
by root 2. Okay.
which
So
is 2 root minus 2 root 2.
Yeah, you can write it as 2 root 2 or keep it as such. Okay.
And
Now
du f
du of f
2
of
1
2, comma 1 is minus
yes.
2, comma minus 2 into the same vector. So you get 2 plus 2
Plus
by
2.
root 2, which is 2 root 2.
Yeah. Plus 2.
And dv of f of 1, comma 2 minus 2, comma 2 dot 1 by 2, comma root 3 by 2, which is
Correct.
minus 1, comma root 3, minus 1 plus root 3, right? Am I correct? Minus, minus 2 plus 2 root 3, right?
Yeah.
Sorry. It is minus 2 plus, I did the simplification straight away actually. It's minus 1 plus root 3 only. Okay?
Yeah.
Fine. And what is dv of f
2
of
1.
2 1?
1. Yeah.
Minus 2 2, 2 minus 2
and 1 by 2 and 3 by 2.
which is
1
minus root,
plus 2.
right?
Correct. And then you find determinant of this matrix.
Yeah. So minus 2 root 2, 2 root 2, minus 1 plus root 3, 1 minus root 3. What is the determinant of this matrix?
Minus 2 root 2 multiplied by 1 minus root 3 minus 2 root 2 bracket minus 1 plus root 3.
Which is?
Which is
It
actually
is 2
1.
root 2. So it is just the negative of the first term you actually see.
Correct.
Right? So it becomes 0. So the answer is 0. Okay, the determinant is 0. So with this, your week 9 topics are over. Week 10 is comparatively easier. So we can complete it quickly. So I guess the topics we have covered in week 9 are clear for everyone. Yes?
Yes, ma'am.
Yes, ma'am.
Ma'am,
So then, yeah.
for the gradient to exist, like it has to be continuous, right? At that point, like when we apply this directional derivative equation.
Yeah, you notice that at the 0 value,
Yeah.
you see,
So yeah,
where is this function?
Yeah.
Where is the g function I described, right? So you see at the 0, it is not continuous, and we saw that the directional derivatives did not exist.
So this side, like, so just. So if we just check the partial derivative, we won't be able to know, right? We have to check if it's.
Yeah, we cannot just by looking at partial derivatives, we cannot say anything. We need the directional derivatives.
Can we use this as a method to check if limit exists or not? Like just using this, like taking the
For
directional
continuity, you want to use directional derivative or the other way around? What is that you are asking?
yeah, for continuity to check, like, will this be like extra work, like, just checking the partial derivative if it's equal to like the directional derivative this way using gradient.
See, yeah, here you can use that, and here either you can use the limit concept, which you again the limit concept, it is more or less again looking like the directional derivative part only, but you cannot use partial derivatives as you told. Okay,
Yeah.
so if the directional derivatives are not existing at some point, then you can question the continuity at that point.
Okay. Like, yeah. Like
Okay.
in this case, if we try to take the directional derivative, we will get a value, right? Like,
But I guess we have given an example for the same question that the directional derivative did not exist except along the x and y axis.
yeah.
I remember we did it in the class. Yeah, this one,
Yeah.
right?
Yeah.
This one or is this similar one, I guess. So you see the directional derivative at 0, 0 did not exist. And what is the example we have used here? It is something different
Yeah,
or the
that's
same.
it's different. It's x
It is
cubed.
a little different, but
Yeah.
you can check about the directional derivative at 0, 0 for this function as well. Okay. So maybe you can try the directional derivative at 0, 0 and tell me what is the result you got, and we can discuss it in the next class based on what is your result. Okay.
Okay, ma'am. So when we define a function like this way, like if xy equal to 0, this way, what are we actually doing? We are just like, is it making the function smoother? What are we doing? Like, it's not making it continuous, right? Getting my
So you are
question.
asking about the directional derivative. You are asking whether it is kind of
No,
helping us to.
when we take a function, like usually when we say function is continuous when it's smooth, right? Like it doesn't have any breaks, right?